To calculate the amperage of a 12-ton HVAC unit with a voltage of 208 volts, three-phase, use the following formula: amps equals power in watts divided by the product of voltage, phase, and power factor. In this scenario, the voltage is 208 volts. The number of phases is 3, since we are talking about a three-phase system. The power factor is assumed to be 0.95, which is typical for HVAC units. The power is equal to 12 tons multiplied by 3.5 kilowatts per ton, resulting in 42 kilowatts. Converting kilowatts to watts, we multiply 42 kilowatts by 1000 watts per kilowatt, which equals 42,000 watts. Now, we can plug these values into the formula. Amps equals 42,000 watts divided by the product of 208 volts, 3 phases, and 0.95 power factor. The product of 208 volts, 3 phases, and 0.95 power factor is 592.8. Therefore, the current in amps is equal to 42,000 watts divided by 592.8. After dividing, we see that a 12-ton HVAC unit with a voltage of 208 volts, 3-phase will pull approximately 70.85 amps. Therefore, a 12-ton HVAC unit with a voltage of 208 volts, 3-phase will pull approximately 70.85 amps. To reiterate the calculation, the formula used is amps equals power divided by the quantity voltage times phase times power factor. Firstly, determine the power in watts, which is the tonnage multiplied by the conversion factor of 3.5 kilowatts per ton, then multiplied by 1000 to convert kilowatts to watts. Secondly, determine the voltage of the system, in this case 208 volts. Thirdly, determine the number of phases, in this case 3. Finally, determine the power factor, which is generally assumed to be 0.95 for HVAC units. To calculate the amperage, divide the power in watts by the product of the voltage, the number of phases, and the power factor. The result will give you the approximate amperage draw of the 12-ton HVAC unit. Let's walk through another example. Suppose you have a 15-ton HVAC unit operating at 480 volts, 3-phase, with the same power factor of 0.95. To determine the amperage, we will use the same formula: amps equals power divided by the quantity voltage times phase times power factor. Firstly, determine the power in watts. This unit is 15 tons multiplied by 3.5 kilowatts per ton to convert to kilowatts. 15 tons multiplied by 3.5 kilowatts per ton equals 52.5 kilowatts. Then multiply by 1000 to convert kilowatts to watts. 52.5 kilowatts multiplied by 1000 equals 52,500 watts. Secondly, we have the voltage, which is 480 volts. Thirdly, we have the number of phases, which is 3. Finally, we have the power factor, which is assumed to be 0.95. Now, amps equals 52,500 watts divided by the quantity 480 volts times 3 phases times 0.95 power factor. 480 volts times 3 phases times 0.95 power factor equals 1368. Now we can calculate the amps by dividing 52,500 watts by 1368. Amps equals 38.38. Therefore, a 15-ton HVAC unit operating at 480 volts, 3-phase, will draw approximately 38.38 amps. Note that this calculation provides an estimate. Actual amperage draw may vary depending on factors such as the efficiency of the unit, the operating conditions, and the specific electrical characteristics of the installation. To get a more precise measurement, it is recommended to use an ammeter to directly measure the current draw of the unit under typical operating conditions. The power factor can vary based on the load and the equipment connected to the system. If the exact power factor is known for the HVAC unit, it is important to use the value in the calculations for a more accurate result. If the power factor is unknown, using 0.95 as an estimate is generally acceptable for HVAC units. Another factor to consider is the starting current of the HVAC unit. When an HVAC unit starts, it typically draws a much higher current than its normal running current. This is known as the inrush current or starting current. The starting current can be several times higher than the running current and can last for a short period of time, typically a few seconds. It is important to consider the starting current when sizing the circuit breaker and wiring for the HVAC unit. The circuit breaker and wiring must be able to handle the high starting current without tripping or overheating. To determine the starting current of an HVAC unit, refer to the manufacturer's specifications. The specifications will typically list the locked rotor amps or LRA, which is the current drawn by the unit when the motor is initially energized and the rotor is not turning. The LRA is the highest current that the unit will draw and is used to size the circuit breaker and wiring. The minimum circuit ampacity or MCA is the minimum ampacity of the conductors required to supply the HVAC unit. The MCA is calculated based on the running current of the unit plus the percentage of the compressor's rated load amps, the RLA. The RLA is the average current drawn by the compressor motor under normal operating conditions. To determine the MCA and RLA of an HVAC unit, refer to the manufacturer's specifications. The specifications will typically list the MCA and RLA on the unit's nameplate. The National Electrical Code or NEC provides guidelines for sizing the circuit breaker and wiring for HVAC units. NEC Section 440.22 specifies the requirements for sizing the branch circuit conductors for air conditioning and refrigeration equipment. NEC Section 440.12 specifies the requirements for sizing the overcurrent protection for air conditioning and refrigeration equipment. When sizing the circuit breaker and wiring for an HVAC unit, it is important to follow the requirements of the NEC and the manufacturer's specifications. This will ensure that the unit is properly protected and that the electrical system is capable of handling the unit's current draw. In addition to the above considerations, it is also important to ensure that the HVAC unit is properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to protect people from electric shock. The NEC requires that all electrical equipment be grounded in accordance with its provisions. To properly ground an HVAC unit, connect a grounding conductor from the unit's grounding terminal to the building's grounding electrode system. The grounding conductor must be sized in accordance with the NEC. It is also important to ensure that all electrical connections are tight and secure. Loose connections can cause overheating and can lead to electrical fires. Regularly inspect all electrical connections and tighten any that are loose. Also, be sure the unit is properly maintained. Regular maintenance can help to prevent electrical problems and extend the life of the unit. It is important to have the unit inspected and serviced by a qualified HVAC technician on a regular basis. The technician can check for any potential problems and make any necessary repairs. Here is another example. Let's say you have a 20-ton HVAC unit operating at 208 volts, 3-phase, with a power factor of 0.9. We will use the formula amps equals power divided by the quantity voltage times phase times power factor. Firstly, determine the power in watts. Since this is a 20-ton unit, multiply that by the conversion factor of 3.5 kilowatts per ton to convert to kilowatts. 20 tons multiplied by 3.5 kilowatts per ton equals 70 kilowatts. Then multiply by 1000 to convert kilowatts to watts. 70 kilowatts multiplied by 1000 equals 70,000 watts. Secondly, determine the voltage of the system. In this case, it's 208 volts. Thirdly, we have the number of phases, which is 3. Finally, we have the power factor, which is 0.9. Now we can substitute the values into the equation amps equals 70,000 watts divided by the quantity 208 volts times 3 phases times 0.9 power factor. Multiplying 208 volts times 3 phases times 0.9 power factor equals 561.6. Now we can calculate the current in amps by dividing 70,000 watts by 561.6. After dividing, amps equals approximately 124.64. Therefore, a 20-ton HVAC unit operating at 208 volts, 3-phase, with a power factor of 0.9 will draw approximately 124.64 amps. Remember to consult the manufacturer's specifications for the specific HVAC unit to obtain the most accurate values for voltage, power factor, and other relevant parameters. These values can vary depending on the specific model and configuration of the unit. Using the actual values from the manufacturer's specifications will ensure a more precise calculation of the amperage draw. Keep in mind the ambient temperature can affect the performance of the HVAC unit. Higher temperatures may cause the unit to work harder and draw more current. Consider this factor when performing amperage calculations, especially in extreme climates. Regularly inspect the electrical components of the HVAC unit, including wiring, connections, and circuit breakers, to ensure they are in good condition. Look for signs of damage such as frayed wires, loose connections, or corroded terminals. Replace any damaged components immediately to prevent electrical hazards. Ensure adequate ventilation around the HVAC unit to prevent overheating. Overheating can cause the unit to draw more current and can also damage electrical components. Keep the area around the unit clear of obstructions and ensure that vents are not blocked. Consider using a surge protector to protect the HVAC unit from voltage spikes. Voltage spikes can damage electrical components and reduce the lifespan of the unit. A surge protector can help to absorb voltage spikes and protect the unit from damage. If you are not comfortable working with electricity, it is best to hire a qualified electrician to perform the amperage calculations and any necessary electrical work on the HVAC unit. Working with electricity can be dangerous, and it is important to take precautions to avoid electric shock. Always disconnect the power to the unit before performing any electrical work. Here are some additional notes. If you are using a generator to power the HVAC unit, make sure that the generator is properly sized to handle the unit's current draw. The generator must be able to provide enough power to start the unit and to keep it running under normal operating conditions. Consult the generator's specifications to determine its power output and ensure that it is sufficient for the HVAC unit. When installing a new HVAC unit, it is important to follow the manufacturer's instructions carefully. The instructions will provide detailed information about the electrical connections, grounding requirements, and other important considerations. Following the instructions will help to ensure that the unit is installed correctly and safely. Also, consider any local electrical codes and regulations that may apply to the installation of HVAC units. Local codes and regulations may specify additional requirements for wiring, grounding, and overcurrent protection. Be sure to comply with all applicable codes and regulations to ensure that the installation is safe and legal. If you have any questions or concerns about the electrical aspects of an HVAC unit, it is always best to consult with a qualified electrician or HVAC technician. These professionals have the knowledge and experience to provide accurate information and guidance. They can also help to troubleshoot any electrical problems that may arise. To summarize, calculating the amperage of an HVAC unit involves using the formula amps equals power divided by the quantity voltage times phase times power factor. It is important to use the correct values for each parameter, including voltage, power factor, and power in watts. Also, remember to consider the starting current of the unit and to follow the requirements of the NEC and the manufacturer's specifications. By following these steps, you can ensure that the HVAC unit is properly installed and operated safely and efficiently.